We have two ways we can use geothermal energy. One, I think we've looked at briefly before, is the idea of geothermal heating, which we could do darn near anywhere on Earth. The other one is generating power with geothermal power, and that's only possible in some places. Geothermal comes from the word geo for earth and thermal for heat. Geothermal is the heat inside the Earth's crust. And it comes from several sources. One is the radioactive materials still in the crust, left over from when Earth formed, that are decaying. They are actually the primary source of heat. Another source of heat is heat that's still left over from when the planet formed over 4.5 billion years ago from a star that blew up. So it's cooling down, but it's still really hot inside. And then gravity causes some pressure at the core. So here is, this picture is a wedge looking through a slice through the Earth. Down in the core of the Earth, it's very, very hot. Up at the surface of the Earth, it's cooler. And the heat gets greater as you go further down in the crust, but you have to go quite a ways to get some temperature. For the first 3 miles of crust, it's not very hot. So what you need if you're going to generate power using geothermal energy is a place where hot, molten magma is close to the surface, and that stuff is super hot. So it's liquid rock is what it is. There are various places around the planet that have that. As you know, probably, Hawaii has some active volcanism, so it's got some places with magma. Iceland has a lot of hot geysers and steam places and active volcanoes, and here is a geothermal plant in Iceland. There is a big hot spot under Yellowstone National Park. There's actually a super volcano under there, a really big one. Our problem is that's a national park, so we can't just go digging power plants there. You are most likely to find magma where you can reach it to generate power at the boundaries of continents. So here at the bottom is a section view from NOAA showing how the crust from the ocean dives down under the crust at the continent, and at that edge, that action creates hot molten magma to rise. And if you look at a map of the Earth here up at the top, you see what you sometimes call the ring of fire. All around the edge, the eastern edge of Asia and the western edge of North and South America are these places where the tectonic plates come together. Those are good candidates. This is a map from the U.S. Department of Energy where they have analyzed the possibility of geothermal energy. Down here, it's kind of hard to see, but down here on the coast of California is where a lot of the U.S. geothermal power that we have is happening. It is this plant here. It's near Santa Rosa, California. It's a place called the Geysers, and you can see steam rising through its cooling towers. So it produces a lot of power. Now, there's a different approach to using geothermal heat. For geothermal power generation, you have to have volcanic magma. It has to be super hot, and you have to go deep. There are some places on the planet where there is some volcanic activity, not enough to generate power, but enough to do other good things. So for example, in Iceland, we mentioned Iceland, most of their homes are heated by geothermal heat. In Klamath Falls in southern Oregon, you know, it can get cold there in the wintertime. They use geothermal heat. They run geothermal lines under their sidewalks to keep the ice melted off the sidewalks. And I think we have talked about the idea of using the uniform temperature that's just a few feet under the surface as a heat source and a heat sink for heat pumps, for passive heating, for passive cooling. So just a few feet below the surface, like 3 to 6 feet down, it's a fairly steady temperature in the mid-50s Fahrenheit. So in the wintertime, you can use that temperature as a heat source. In the summertime, you can use that temperature as a heat sink, giving off heat from your building. And so, what many people do is dig pipes into the ground that they run liquid through. You can run pipes horizontally, and the advantage to that is there's not as much excavation. You don't have to go down as deep. The disadvantage is you have to have a lot of land. The other choice is go vertically, like this diagram shows. That doesn't require much land, but it requires cost for excavating those deep holes, which may be a few hundred feet deep even. Here's a picture of LCC's Child Care Center. They are using this kind of uniform heat from the earth. Here are a couple of pictures from the LCC Downtown Campus. So the top picture here is in the lobby of the campus looking out across the street towards the public library. And this is one of their energy analysts who's talking about what's in this glass window here in the floor. And then the bottom picture is a close-up of that glass window in the floor. That lets visitors see how the LCC Downtown Center is using geothermal ground source heat and cooling to pre-chill its chilled water and to preheat its heated water. They dug, I forget, well, I'm not going to say how many of these tubes they dug. I think they're like 300 feet deep. There's a lot of them. All right, geothermal.